Hi friends, I am Sneha. Welcome to this session. So in this lesson we are going to start with concept Laplace transforms. Actually this concept is from signals and systems subject, but it plays an important role while solving the problems of control system. So let us see the Laplace transform concept. Basically an LTI system or any LTI system is defined by using differential equations. So differential equations are nothing but equations in time domain. But while solving these differential equations, that too higher order differential equations, it is difficult and also it is time consuming. So what we are going to do is we are going to convert these differential equations to algebraic equations. So in order to solve the higher order differential equations, we are going to convert those differential equations to algebraic equations, and Laplace transform is a tool which we are using to convert the differential equations to algebraic equations. That means Laplace transform is used to solve the differential equations by converting them to algebraic equations, which is nothing but Laplace transform is converting time domain functions or time domain signals or time domain equations to frequency domain signals. So we are using this Laplace transforms tool for converting differential equations to algebraic equations, which is nothing but for converting time domain signals to frequency domain signals. Let us consider x of t be the time domain signal and x of s be the frequency domain signal. Now, by using Laplace transform, we will see how to convert this time domain signal x of t to frequency domain signal x of s. So, the Laplace transform of a time domain function x of t or time domain signal x of t is defined as Laplace transform of x of t that is equals to x of s that is equals to integral minus infinite to infinite x of t e power minus st dt. So this is the formula which we are going to convert the differential equations to algebraic equations or time domain signals to frequency domain signals. So in order to transform a given function of time x of t into its corresponding Laplace transform x of s, first we are going to multiply the time domain signal x of t by complex exponential signal e power minus st, where s is a complex number which is equals to sigma plus j omega. So we are going to multiply the given time domain signal x of t by complex exponential signal e power minus t, where s is a complex number which is equals to sigma plus j omega, and we are going to integrate the entire product x of t into e power minus st with respect to time with limits from minus infinite to plus infinite, and this entire integration results in Laplace transform of x of t, that is x of s. So this x of s is nothing but Laplace transform of x of t, where L is nothing but Laplace transform operator. So this Laplace transform operator helps in converting or transforming the time domain function x of t to frequency domain function x of s. So this is about Laplace transform, which is converting differential equation to algebraic equation or time domain signals to frequency domain signals. And the original signal, that is time domain signal x of t, can be obtained back from x of s signal, which is nothing but frequency domain signal, by a process called inverse Laplace transform. So by using the process called inverse Laplace transform, we can obtain the original time domain function from the obtained frequency domain signal, and it is denoted by L inverse. So L inverse is the inverse Laplace transform operator. Inverse Laplace transform operator. So we can say that L inverse of Laplace transform of x of t, which is nothing but L inverse of x of s, is equals to x of t. That is, from frequency domain signal we can get back the original time domain signal by using inverse Laplace transform. And the formula for inverse Laplace transform of x of s is defined as x of t is equals to 1 by 2 pi j integral sigma minus j infinite to sigma plus j infinite x of s e power st ds. So this is the formula which helps in retrieving back the original time domain signal x of t from the frequency domain signal. So by using the inverse Laplace transform, we can convert the frequency domain signal to time domain signal, and this both x of t, that is time domain function, and x of s, that is frequency domain signal, forms a Laplace transform pair. Laplace transform pair, that is x of t and x of s forms a Laplace transform pair, because from x of t, by using the process called Laplace transform, we can get x of s, and from x of s, by using the process called inverse Laplace transform, we can get the signal x of t. So both x of t and x of s forms a Laplace transform pair. So this is all about the basic introduction to Laplace transform. How to obtain the Laplace transform of a signal and also inverse Laplace transform of a frequency domain signal. Now we will see some Laplace transform pairs or Laplace transform of commonly used signals like unit step, unit ramp, unit parabola, and also exponential signals, real exponential signals, complex exponential signals. So we are going to see Laplace transform of commonly used signals, or also called as Laplace transform pairs. So firstly, what we are going to see is, we are just going to see the end result of Laplace transform of signals. Okay. So the first Laplace transform pair is Laplace transform of impulse signal. So Laplace transform of impulse signals, that is del of t is 1. And the next Laplace transform is, Laplace transform pair is Laplace transform of unit step function, which is equals to 1 by s. And the next Laplace transform pair is Laplace transform of ramp function. So Laplace transform of ramp function is 1 by s square. And Laplace transform of parabolic function, that is t square into u of t, is 1 by s cube. If you observe these three signals, that is Laplace transform of u of t is 1 by s, Laplace transform of t into u of t is 1 by s square, and Laplace transform of t square into u of t is 1 by s cube. So from this we can write, or we can generalize it as, Laplace transform of t to the power of n u of t is n factorial by s to the power of n plus 1. Now we will see the Laplace transform of real exponential function, that is e power at u of t. So Laplace transform of e power at u of t is 1 by s minus a, and Laplace transform of e power minus at u of t, which is nothing but the decaying real exponential signal, is 1 by s plus a. And now we will see the Laplace transform of complex exponential signal e power j omega t u of t. So Laplace transform of complex exponential signal e power j omega t u of t is 1 by s minus j omega. And Laplace transform of e power minus j omega t, which is decaying complex exponential signal, is 1 by s plus j omega. The next Laplace transform pair is Laplace transform of t into e power at u of t, which is equals to 1 by s minus a whole square. So from this we can generalize Laplace transform of t power n e power at u of t as n factorial by s minus a whole to the power of n plus 1. And now we will see the next Laplace transform pair, that is Laplace transform of sine and cosine functions. So Laplace transform of sine omega t u of t is omega by s square plus omega square, and Laplace transform of cos omega t u of t is s by s square plus omega square. And next Laplace transform pair is Laplace transform of t into sine omega t u of t, which is equals to 2 omega s by s square plus omega square. And Laplace transform of t into cos omega t u of t is s square minus omega square by s square plus omega square. And next Laplace transform pair is Laplace transform of damped sine and cosine functions, that is e power minus at sine omega t u of t. So Laplace transform of e power minus at sine omega t u of t is omega by s plus a whole square plus omega square, and Laplace transform of e power minus at cos omega t u of t is s plus a by s plus a whole square plus omega square. And the next Laplace transform pair is Laplace transform of hyperbolic sine and cosine functions, which is equals to omega by s square minus omega square. That is Laplace transform of sin h omega t u of t is omega by s square minus omega square, and Laplace transform of cos h omega t u of t is s by s square minus omega square. And next Laplace transform pair is Laplace transform of damped hyperbolic sine and cosine functions, that is e power minus at sin h omega t u of t is omega by s plus a whole square minus omega square, and Laplace transform of damped cosine signal, hyperbolic cosine signal, that is e power minus at cos h omega t u of t is s plus a by s plus a whole square minus omega square. And next Laplace transform pair is Laplace transform of sine omega t plus theta. So Laplace transform of sine omega t plus theta is s sin theta plus omega cos theta by s square plus omega square, and Laplace transform of cos omega t plus theta is s cos theta plus omega sin theta by s square plus omega square. So these are all the Laplace transform pairs. So all these Laplace transform pairs are nothing but Laplace transform of some commonly used signals. So Laplace transform of impulse signal is 1, or we can also say that inverse Laplace transform of 1 is impulse signal, and Laplace transform of unit step, that is u of t, is 1 by s, or we can also say that inverse Laplace transform of 1 by s signal is u of t, and Laplace transform of t into u of t is 1 by s square. Laplace transform of t square into u of t is 1 by s cube, and Laplace transform of e power at u of t signal is 1 by s minus a. Laplace transform of e power minus at u of t signal is 1 by s plus a. So these are all these Laplace transform pairs are the end results of the Laplace transform of signals. So in order to get the signals, we need to perform the Laplace transform process on the given signals, and there is no need of that process for this subject, because we just use these end results or Laplace transform pairs as formulas while solving the problems, and for the process we can see them in signals and systems subject. So first, for this subject, just remember this end results of Laplace transform pairs. Now the next topic is Laplace transform properties. So we will just see few Laplace transform properties. Actually, these Laplace transform properties and theorems may not be useful while solving problems, but they were asked directly in GATE papers. So try to remember these Laplace transform properties also. So the first property is linearity property, which is nothing but Laplace transform of a x1 of t plus b x2 of t is equals to a x1 of s plus b x2 of s. So this is the first property of Laplace transform, which is nothing but linearity property. So linearity property of Laplace transform states that weighted sum of two signals is equal to the weighted sum of individual Laplace transforms, where x1 of t and x2 of t are functions of time and a and b are constants. So this is the linearity property of Laplace transform. Next property is derivatives property of Laplace transform. So derivative property of Laplace transform states that Laplace transform of dy dt of x of t, that is first derivative of x of t, is equals to s into x of s minus x of 0 minus. Here x of 0 minus is nothing but x of 0 minus or x of 0 plus is nothing but x of t at t equals to 0. So Laplace transform of dy dt x of t is equals to s into x of s minus x of 0 minus, and Laplace transform of second derivative, that is d square by dt square of x of t is equals to s square x of s minus s into x of 0 minus x dash of 0 minus. X dash of 0 minus is nothing but first derivative of x of t at t is equals to 0, and Laplace transform of d cube by dt cube x of t is equals to s cube x of s minus s square x of 0 minus s into x dash of 0 minus x double dash of 0 minus. X double dash of 0 minus is nothing but second order derivative of x of t at t is equals to 0. So this is the property of Laplace transform which states the derivative property or differentiation property of Laplace transform. So just remember that Laplace transform of d by dt of x of t is equals to s into x of s. And third property is integral property of Laplace transform. So Laplace transform of integration of x of t, that is integration of time domain function, is x of s by s plus x inverse of 0 plus by s. Here x inverse of 0 plus is nothing but integration of x of t at t is equals to 0. Laplace transform of double integral of x of t is equals to x of s by s square plus x inverse of 0 plus by s square plus x to the power of minus 2 of 0 plus by s, and Laplace transform of triple integral of x of t is equals to x of s by s cube plus x inverse of 0 plus by s cube plus x to the power of minus 2 of 0 plus by s square plus x to the power of minus 3 of 0 plus by s. So this property is nothing but the integrals property of Laplace transform. So just remember, Laplace transform of integration of x of t is equals to x of s by s. And the next property is differentiation in s domain. That is Laplace transform of t into x of t is equals to minus d by ds of x of s. So this property indicates that differentiation in s domain. And the next property which you need to remember is frequency shift property, which is nothing but Laplace transform of e power minus at x of t is equals to x of s plus a. So this is frequency shift property of Laplace transform. So same like Laplace transform pairs, remember these Laplace transform properties too. Now we will see two basic Laplace transform theorems. These were asked directly as questions in GATE papers. So try to remember these two theorem results too. So the first theorem of Laplace transform is initial value theorem. So initial value theorem of Laplace transform states that limit t tends to 0, x of t is equals to limit s tends to infinite, s into x of s. And next theorem of Laplace transform is final value theorem. So final value theorem of Laplace transform states that limit t tends to infinite, x of t is equals to limit s tends to 0, s into x of s. So remember these two Laplace transform theorems and these properties along with Laplace transform pairs. So that's it for this lesson. I hope I am clear with my explanation. So thank you for watching this lesson. Have a great day.